Dear students, welcome to our class on Micrometeorology of Crops, Temperature 1. Micrometeorology of Crops, Temperature 1. When we say micrometeorologically, temperatures are of two. One is the air temperature, second one is the soil temperature. If we don't mention specifically soil temperature, it always refers to air temperature. This is the fundamental and basic. Now, by definition, temperature is defined as measure of speed per molecule of all the molecules of a body, whereas heat is the energy arising from a random motion of all the molecules of the body. So, what is the meaning of it? Temperature measures the energy of the average energy of individual molecules. Temperature measures the average energy of individual molecules, whereas heat measures the total molecular energy. That's why the units are ergs, joules for heat, temperature, degree centigrade, Fahrenheit, Kelvins. Now, see here, every body, B-O-D-Y, every body, not everybody, every body on this earth goes on absorbing, goes on reflecting, goes on emitting as long as sun is there. As long as sun is there. Even in the absence of the sun, the long wave radiation is released because during the daytime, earthly bodies or terrestrial bodies absorb. So, during the night time, they go on losing it. As I said in the previous classes, short wave radiation, long wave radiation. What is short wave radiation? It starts from gamma rays. Of course, light part of the spectrum is there and near infrared is there. So, it is up to 3 microns. From 3 microns to 100 microns, long wave radiation. The sun also sends long wave radiation. The sun also sends long wave radiation. It falls on the earth. Suns, however, that long wave radiation is not that much as compared to the long wave radiation emissions, okay, from the earthly bodies, because the short wave radiation, when it is falling on the earthly bodies, it is absorbed, something is reflected, no doubt, it is absorbed and emitted. So, those long wave radiations are very, very important with reference to micrometeorology. However, as I said in my previous class, Professor J.L. Monteith and Swinbank, they tried. Upward movement of the long wave radiation, Monteith had developed, Professor J.L. Monteith, and of course I was fortunate to learn from him in the University of Nottingham, Sutton Bonington, Loughborough, UK. Now, Swinbank, he had developed techniques for a downward movement of the long wave radiation. So, actually when long wave radiation is coming from the sun is sending the energy, what happens? Sun is sending the energy. Now, exosphere, okay, troposphere, stratosphere, mesosphere, ionosphere, exosphere, ionosphere, mesosphere, okay, stratosphere, troposphere. When it is coming, CO2, O2, water, H2O, all these things are present in addition to basic O3 that is present in between approximately 30 and 55 kilometers from the surface of the earth, okay, ozone layer that filters the ultraviolet radiation. Now, why I am telling all these things is that everybody, now when we are talking of micrometeorology of temperature, where we get from that? So, temperature by definition I told, heat by definition I told, temperature, when sun's energy is coming, long wave radiation, it heats. From after it is falling on the earth, earthly bodies or terrestrial, they release and the atmosphere gets heated up. Now, please understand that it is absolutely difficult. What are the incoming long wave radiations? What are the outgoing long wave radiations? It is very difficult. It is absolutely difficult. Still, Professor J.L. Monteith, Professor Swinbank, upward Professor J.L. Monteith, downward Swinbank have defined and they have given for cloudless day at 0 degree centigrade. Depending upon that, we can derive it. Now, why I am telling you this particular long wave radiation exchange, please write an important point here. Please write an important point here. Long wave radiation transfer. Long wave radiation transfer is important. Long wave radiation transfer is important in determining the thermal or temperature relationships of crop plants, and their environment. The meaning of it is long wave radiation exchange. As I said 1 minute back, long wave radiation, okay, even in the absence of the sun. Say for example, light is falling on me, okay, now sun is absent now. Even now also long wave radiation is emitted, because during the daytime the terrestrial bodies are sinks, acts as sink, and then during the night time they are releasing it. Now here another important thing is coming to an important Wien's law. Okay, Wien's law. What is Wien's law? I told basic definition. Just here only application point of item. See, the sun may be considered as a perfect black body. It may be considered because, the peak wavelength of emitted radiation, please write, the peak wavelength of emitted radiation, from the sun is 0.48 microns. 0.48 microns. It is related to absolute temperature of the sun, that is 6000 kelvins, 6000 as described by Wien's law. Now you may put a question, why Radha Krishnamurthy is telling Wien's law here? Now see, earthly bodies this is the crop. This crop at a temperature of 20 degrees centigrade or 293 kelvins, okay, it emits, okay, like the sun at 0.48, the crop in an acre field or a hectare field or a forest, 9.89 microns, okay. Peak emission is at peak emission of 9.8 microns is at 20 degrees centigrade, okay. Now here the application I will tell, this bit will come for most of the crops, whether it is oilseed, pulses, cereals or forestry crops. They perform excellent at 20 degrees centigrade. This is one of the reasons. What is this? This reason is at 293 kelvins or 20 degrees centigrade, the peak of the emission by the crops takes place. So that's why that is the optimum temperature for biomass production. It is the optimum temperature for flowering. It is for most of the crops. Okay, that is what. Now from here we go to another important thing, that is visual temperature. Of course, this is you may have learnt it even in the in 8th class, 9th class or 10th class. What is visual temperature? The visual temperature is defined as the temperature for any given pressure. The temperature for any given pressure at which a sample of dry air, please write, at which a sample of dry air would have the same density as moisture. It is a comparison between the dry air and moisture. Okay. Now here, why I am telling here the temperature, visual temperature is that now the temperature of what we are very much concerned, the agrometeorologists are concerned with temperature of the Earth's surface. 1/3 is the lithosphere, that is the land portion, 2/3 is the water. We, the agrometeorologists, are concerned with the Earth's temperature, because micrometeorology, temperature 1, you should know it. Now, first I read the statement, then I explain. No need to write, I explain to you. Temperature of the Earth's surface is primarily controlled by the influence of the sun and the properties of the atmosphere. Temperature of the Earth lithosphere. No, I am not saying no water. Okay, let us confine to, the agrometeorology confine to only for lithosphere part. Now, the temperature of the surface is controlled by sun and atmospheric properties. This is the first statement. Then I will add not only earth, not only sun, not only atmosphere, but also time of the year. Next statement I will add. What is that? What is that? The earth is approximately a spherical body at a large distance from the sun, and so the sun has different apparent elevations when viewed from the earth's surface at different latitudes. 0, equator latitudes are increasing, north and south. Now, elevation of the sun, apparent view from the latitudes, if you see, elevation of the sun play an important role with reference to what? With reference to Earth's surface. As I said previous, what is the second? Properties of the atmosphere. The third one here, the time of the year. Okay, the time of the year, because we have 4 seasons. Okay, as I said, fundamentals I need not say it. The spring, the winter, the fall, the summer. Okay, all these seasons. So depending upon these, elevation of the sun, time of the season, in between, the properties of the atmosphere determine the temperature of the earth, because crops are there on the earth. Now here I would like to enlighten you one more important point, that is, please note that okay, the majority of the croplands, please write this bit will come 100% certain for JRF, SRF, even in the interviews will be asked. The majority of the croplands are confined to dash temperature, this bit 0 to 40. What is the explanation for that? In the interviews, net after net, you will be asked, you are an agrometeorologist, you are telling that 0 to 40%. Why? Now, if it is below 0 degrees centigrade, this is the range in which most of the croplands, not organisms, croplands confined to. Because if it is less than 0, what will happen? Water gets solidified. In most of the crop plants, water constitutes 90%. So in the leaves of the the cells contain 90% of the water. Okay, that particular 90% water, when less than 0 degrees centigrade, what will happen? Solidifies. When it solidifies, desiccation occurs. Cells die. Internal structure dies. If it is more than 40, sun-clad, stem girdle, desiccation, similar things happen when temperature is high. So most of the plants are confined to, as far as temperature drops. This bit is come temperature 1, you must remember. Now here another important thing, isothermal change. First please write one line. I am going to complete this class in 2 minutes. Isothermal change. Please write, this bit will come in the GRF. That's why. A change in the pressure, volume and or density. A change in the pressure, volume or density of some portion of the atmosphere. Troposphere, stratosphere, mesosphere, ionosphere, exosphere. Now, the change in the, please tell me, the change in the pressure, volume or density of some portion of the atmosphere under observation, when what we are observing, which takes place without any change in temperature. Without any change in the temperature, we call it as the isothermal change. Why? We should know in the micrometeorology of this particular point is that the vertical motions of the rising air. Now here I would like to explain on a small the vertical motions of the air. Passes. Okay, air passes. Vertical motions. Okay. Now what is happening in the vertical motions of rising or falling packets of air? Falling packets of air. Air we cannot see. That's why packets of air. Okay. Are often sufficiently rapid to ensure that temperature changes are due to temperature changes of the packet of air. Temperature 20, 21, 19. Some changes are occurring in the parts of the air. These temperatures changes of the parts of the air are due to first internal changes. Okay, expansion or contraction of the air resulting from the pressure changes. Okay. 980 millibars, 981 millibars, something like that, So when pressure is changing, the expansion or contraction of the air particles takes place. That's why the temperature of the air particles will change. Please write another important point. The major part of the solar irradiance, is absorbed at the surface of the earth. Major part of the solar solar irradiance. What is irradiance? I told several times. I also tell you after you write. So major part of the solar irradiance is absorbed at the surface of the earth, and temperatures are generally greater in this region. And temperatures are greater in this region, where on the surface of the earth, and decrease with increasing height. And they decrease with increasing height, particularly with reference to the troposphere. That's what we call it as the lapse rate. The definition will come here. The rate of change of temperature is known as lapse rate. Now, see here, the major part of the solar irradiance. There are three words that I learned from Professor J.L. Monteith. One, radiation flux. Flux means flow of radiation, energy. Okay. Radiant flux density. What is when you add area, how in particular unit area for radiant flow, radiant flux. What is irradiance? When you add time factor to that. Flow, space and time factor. So flow, radiant watts, second one watts per meter square, watts per meter square per second. So radiant flux. Radiant flux density irradiance. What this is the irradiance. The part of the solar irradiance is absorbed at the surface of the earth. That's why the temperature of the earth goes. Now I would like to discuss with you last half minute one very interesting thing. Adiabatic change. Adiabatic change I would like to explain. Earlier I have explained from the micrometeorological point of view. I explain for only half minute. What is adiabatic change? The rate of change of temperature due to rate of change of pressure. We call it as basic definition is adiabatic change. dq is equal to du plus pdv. dq is equal to du plus pdv. What is dq? Heat supplied to a system. Heat supplied to a system is equal to increased internal energy. What is the internal energy increase in the system plus some external work? It does some external work. What is the external work? Going up, going down. So pressure changes, temperature changes. So some work is done. So adiabatic change is very, very interesting. What is adiabatic change? Heat supply dq is equal to increased internal energy du plus some external work pdv. Now temperature changes are due to expansion or contraction. That's what I told of air, expansion or contraction of the air by external force. So this much I will have to discuss with you in the first class of the temperature with reference to micrometeorology of the crops. Thanking you for your patient hearing.